So, let us get started with the foundations of multirate systems, multirate signal processing. So, the motivation towards this area is in two main problems coming from engineering practice. One is sampling rate converters and the other is in oversampled systems. So, let me brief you with a motivation towards multirate signal processing. Now, the foundations to multirate signal processing is basically you are sampling the standard Nyquist sampling theory, right. So, the question way back in the 1960s, 1970s when people in Bell Labs were developing systems were as follows. For example, in those days the digital audio required various sampling rate options. For example, if you think about the studio work, that required a sampling of 48 kilohertz for audio. If you were to think of the digital tape / CDs, then they required a sampling rate of 44.1 kilohertz, and if you thought about broadcasting applications, that required say 32 kilohertz. The question is, how can I go from an analog signal and cater to 3 different systems that are working at different sampling rates, right. So, how can I cater to a digital system working at different sampling rates with the same analog signal, it is the same continuous time signal, but it is working at different sampling rates. Now, a naive solution one can think about is, well, I have digital, I will convert again digital to analog, I do the sampling again, right. I have these D to A to D converters at every point in the configuration, and therefore I work with these systems, right. A naive solution is use ADCs and DACs at every point where a conversion is needed. But there is also a cost. You cannot buy these ADCs very cheaply, it is not possible to buy them, right. So, that is prohibitive. If you have various systems which require different sampling rates, I can't use ADCs and DACs at every point in the system. So, therefore, we need to do something clever. Basically, we manipulate digitally somehow that we can go from one sampling rate to the other sampling rate, that is, I can convert my sampling rate seamlessly from one rate to the other still preserving all the properties of the underlying original signal that I have, and then work with the rest of the system, right. So, that is the solution, but how to go about doing that? So, that led to the birth of this theory into multirate signal processing, and a lot of work has been done from the pioneering works of folks at Bell Labs, Ron Crocier, Belanger, and many of these people who were there at that time, and then this has led into a lot of applications from compression to high decimation filter design to transmultiplexers and so on and so forth. The applications are tremendous, and today I think this is something basic. So, it is almost like 40-50 years, but I think it is basic. Now, with this motivation in mind, let us see what are the basic operations in multirate signal processing. So, when we say multi-rate, we mean that we are changing the sampling rate. So, the idea is clear. Now, if you think about what possible operations are there, the first operation is decimation, which means I am downsampling or I am reducing the sampling rate, right. We can assume it is an integer level of decimation, right, because anything which is a fraction we can always realize as some combinations of increase and decrease of the sampling rate, right. If you think about decimation, pure decimation, let us think about integer decimation. That means I am reducing the sampling rate by say rate half or 1/3, 1/4, some number, some integer decimation. Then we have this expansion, which is we are upsampling or we are increasing the sampling rate by again an integer amount. Okay. Now, if I want to get a rate of say 1.5 conversion, 1.5 is 3/2, right. That means I can reduce the rate by half and increase the rate by 3. I mean decimate by 2 and expand by 3, and that might give me the rate that I need, right. So, again let us go back to our motivation to the studio work at 48 kilohertz, and then which required for the CDs at 44.1 kilohertz. The rate conversion is right 44.1 upon 48, or if you want to go from other side you can say 48 upon 44.1, whichever is the way you want to go about, right. So, the goal is I do not want to use ADCs in the middle, directly using the samples that I have in whichever sampling rate I started off with. I want to proceed to convert seamlessly from one domain to the other domain. Now, let us go a little deeper with this idea in mind, and we will say what is this M-fold decimator. So, an M-fold decimator takes x of n, which is my discrete set of samples as its input, downsamples by a rate m, and I get my decimated output, which is Yd of n, and this is also called a compressor. Yd of n is basically x of m times n. So, this is the relationship. So, let us see how this works. right. So, let us say I have samples. One, say 2, this is say 1, say this is 0.5, and let us assume that this is time step 0, time step 1, time step 2, time step 3. And if I want to get this through a decimator with m equals 2, that means I am slashing my rate by half, right. What I get is, so just look at this equation, that means I take the first sample, I discard the second one, I take I retain the third, I slash the fourth. So, every alternate sample I just chuck it off, right. So, basically I get this. This is the output of a downsampler by 2, decimation by 2. If I decimate by 3, then I retain 1 in 3 samples. So, I think this idea of decimation has some historical perspective. I do not know how true this is right or wrong, but imagine if you had a crazy military general and who decides to retain one soldier among 10 soldiers in the enemy camp, right. I mean, that is 1 in 10 decimation. So, I think that is probably the idea of decimate, 1 in 10, 1 in 10 heads is kept, right. So, it is basically you are slashing the rate, number of people you are getting them out, right. And probably here the same thing with sampling, that means you retain 1 in 10 samples, but of course we want to be very general for downsample by m, that means we retain 1 out of m samples. Okay. So, similar to the decimator, we have another important block which is an L-fold expander, and let us see what this expander does. It is also called upsampler. So, we have x of n as our input, we want to upsample this by a factor of L, and let us say we get this signal y e of n, e standing for the expander, and like the decimator we can go about with a relationship between y e of n and x of n, and y suffix e of n is x of n upon L if n is an integer multiple of L and this is 0 otherwise. So, let us see what is happening with the expansion process. Suppose I give you samples, time index 0, 1, 2, and let us say the values are 1, 2 and 3. And it goes through an expansion by 2 what we do is the following. So, we retain 1 at the next time step I have a 0 because it is 0 otherwise, then I retain 2, 0 otherwise, retain 3, 0 otherwise. And this happens, which means I am inserting these zeros at these points at alternating points, right. I mean, this is because it is upsampling by 2 and my rate has now sort of doubled. Okay. Now, you may ask these questions as I am lecturing, I mean, there is no information that you are really conveying, right. I mean, you just have the same information here except that you have doubled and you have placed these zeros. But usually these operations of expansion or downsampling or upsampling, they have some filtering operations as well. So, once you upsample, you can imagine I need to have some interpolation filters to fill in these samples, fill in these zeros, right. What sort of interpolating filters would I use, and can I get reconstruction which is perfect, and these type of questions, these are things which we will discuss through the succeeding modules in this succeeding lectures in this module on multi-rate signal processing, because this is basically the idea, right. How can we construct filter banks, etc. Basically I have a signal, digital signal, I just pass them through some analysis filters, I reduce the sampling rate, then at that point I am doing some transmission with quantization or quantization and transmission, right. And then at the receiving side I basically upsample to restore my sampling rate back, and then I have to have, because upsampling itself, this process does not let you get the samples that you want, and then you should have some interpolation filters. So, this is sort of the sketch of the idea what we need, right. But we studied 2 basic operations on decimators and expanders, and we want to basically delve a little more deeper into these ideas. But here I think I would like to sort of give you a simple exercise for thought, not so difficult. Verify that decimators and expanders are linear but time varying. This is very important. They are not LTI, but this is an LTV operation, they are LTV systems. Okay, it is not too difficult to verify this, and you could do that.